everybody, so today I'm going to talk to you about the rest of KSP. We'll talk about comparing solubilities of different salts and also common ion and also forming a precipitate, and then we'll go back and we'll quickly address Le Chatelier's principle and how that relates to something called the common ion effect. So with KSP, there's two types of problems where they'll ask you to compare solubility. So let's say that I had two salts like I had AgF, and then I had another salt like barium chromate. Now when these dissolve in water, both of them form two ions. This would form Ag plus and F minus, and this would form Ba plus 2 and CrO4 2 minus. So both of them form two ions. When they both form the same amount of ions, we can compare the solubility of these ions using KSP directly. So I can look at the KSP of both of them and determine which one's more soluble. Let's say AgF's KSP was 1 times 10 to the negative 10th, and let's say BaCrO4's solubility was 1 times 10 to the negative 12th. And I could say what's more soluble? Well, AgF has a larger KSP, and so AgF would be more soluble. And I can do this because their KSP expressions are the same. They both produce two ions. If I had something where I had AgF and then I was trying to compare that to PBI2, and we have the KSP of AgF as 1 times 10 to the negative 10th, and we have the PBI2 maybe as 1 times 10 to the negative 13th. If I had these two, I could not compare their KSPs the same. Why couldn't I compare their KSPs the same? They form different number of ions. The expression for AgF in terms of x would be x squared. The KSP expression in terms of x for PBI2, if we worked it out, would be 4x cubed. Because of the different number of ions, we would need to compare them based on their molar solubility. So for this problem up here, for the AgF and the PBI2 problem, we would actually need to solve for x. Once we solve for x, then we can compare x, and see which one is going to be more soluble. So when we do this, we get AgF as 10 to the negative 5th molar for AgF as our x value. But when we do this for PBI2, and I'll grab a calculator, so when we do this for PBI2, we'll have e to the negative 13th divided by 4, and then raised to the 1/3 power cube root. And in that case, we get 2.9 times 10 to the negative 5th. 2.9 times 10 to the negative 5th molar, and that's for PBI2. Now look at that. PBI2 actually has a higher solubility. PBI2, even though it had a smaller K value, its X value, its molar solubility is actually higher. And this goes straight to the point here. You can't compare the KSPs directly for this. Okay, let's move on to the next part, which is effect of a common ion on solubility. And when we put a common ion into a solution that already contains an actual insoluble salt, the solubility will go down. Does the solubility go down of this particular salt, or any salt for that matter? Well, let's look at how common ion works with this example down here. What ends up happening is that if I were to have a salt, like for example lead 2 chromate that I mentioned right here in this example, the lead 2 chromate, it will break up into these ions, Pb plus 2 and CrO4 2 minus. If I were to add another salt that contained the same ions, either chromate or lead, like for example if I were then to add some sodium chromate, adding sodium chromate to the lead chromate increases the chromate. If I increase the chromate, that will cause the amount of chromate to increase. As a result, it would shift back to the left side of the reaction, and that left side of the reaction would be producing the PbCrO4 solid. So whenever you add a common ion, an ion from another salt that is the same as an ion that already exists, at that point, it will shift the equilibrium back to the left. What will be the result of this stress is that the concentration of Pb+2 will decrease considerably. And we can see that in this example right here. Here's my zinc hydroxide, which is insoluble. They want me to calculate the concentration of zinc in this. So I write out my equation, and I get Zn+2 plus 2OH minus. And now we have x and 2x. If we put that into KSP, we'll have KSP equals 4x cubed. And if we solve for x using the KSP up here, we can do that right now, and we would get 7.7. We would get 7.7 e to the -17th divided by 4, and then taking the square root of the cube root of that, we would get 2.68 times 10 to the -6th. And that's my zinc, my X value there. Now let me show you how to set this up with a common ion, what would happen. So we'd have our same equation that we would have above, up here. We would have our zinc forming our zinc +2, zinc hydroxide forming Zn+2 plus 2OH minus. Our zinc would start off at 0, but now they're telling us in this problem that we have 0.1 molar NaOH. So instead of starting at 0, we would have 0.1 molar OH minus. Now we'd have plus x plus 2x, and then we would have x and 0.1 plus 2x. Now, this is a very small k value. It's the same k value that we had up here, the 7.7 times 10 to the -17. But what I can do now is I can eliminate this 2x. I can neglect it. So now when I look at this in my KSP, I'm going to have my KSP equals x for the zinc times 0.1 squared equals the KSP. So 7.7 times 10 to the -17 equals 0.01x. If I divide both sides by 0.01, then I will get 7.7 times 10 to the -15th molar. Now let me highlight these two responses here, okay? We have the original zinc here, and then we have the zinc down here, these two highlighted results. Look at what happened to the solubility. The Zn+2 dropped from 10 to the -6 all the way down to 10 to the -15. When you add a common ion, it pushes the reaction to the left, and it causes a suppression of the solubility. Okay, the last thing is determining if a precipitate forms for the KSP model. And so let's say that I were to react two salts, like if I were to react AgNO3, which is soluble, and I were to react that with Ki. When these react together, they form the precipitate AgI, and they also form KNO3, but we're looking at this. You'll be given a KSP for this, so KSP for AgI, we'll keep it an easy number to work with, so like 1 times 10 to the -12, let's say. And they'll ask you, does a precipitate form if I mix these two together? And your first inclination is, well, yes. But the thing is that you need to have enough ions present for a precipitate to form. Let's say, for example, with the AgNO3, let's say that I use 50 milliliters of it and 0.001 molar. And let's say for Ki, I do 50 milliliters and I do 0.0001 molar. Now, I'm going to add these together. So I'm going to have a total of 100 milliliters. I basically diluted them out. So instead of just having 0.001, I've diluted out the AgNO3. So the new AgNO3 is going to be half. We've made the volume double. This is going to become 0.0005 molar. And this I is going to be 0.00005 molar. You could do this, and I'm not going to spend a lot of time doing this because the video is running long. You could do M1V1 equals M2V2 for all of these, and it will work, and you'll get half the concentration. Now, what I could do is I could take these values. KSP equals Ag plus times I minus. And I could do it two ways. I could solve for x and compare it, or I could plug these values in. Let's plug these values in. When I plug the values in, it's called QSP, because not at equilibrium, we don't know yet. Ag was 0.0005. I was 0.00005. And now let's just multiply them together and see what we get. So we're going to get 0.1235 times 0.12345. And we're going to get 2.5 times 10 to the negative 2468. Now look, this number that I just got here, this number is larger than the KSP. The KSP for this, we said, was 1 times 10 to the negative 12th. When this is larger, when QSP that we just solved for is larger than KSP, then a precipitate forms. What this is telling us is that there are enough ions present for a precipitate to form. Now we'll practice more of these in class, and I'll put up a sample of a common ion one and a QSP versus KSP for homework to do along with watching the video. Now one last thing that I want to cover in the last 2 minutes or so is going back to Le Chatelier's principle, common ion effect. The common ion effect, if you increase the concentration of an ion by adding it to a solution, this causes a shift to the right. I'm sorry, it's not true. Shift to the left, and a decrease in solubility. Forcing a reaction to completion, with Le Chatelier's principle, we can do this in a few ways, but one way that is most popular to do it is to actually remove product as it forms. So if we had a reaction like N2 plus 3H2 yields 2NH3, and we want to form ammonia gas, well, one way to form ammonia gas is to remove it as it forms. If we decrease the ammonia gas as it's forming, there won't be a reverse reaction occurring, and the reaction will be forced to head in only one direction, which would be the forward direction. Lastly, catalysts affecting an equilibrium. Catalysts will affect the equilibrium by doing nothing to it. So a catalyst, it will speed up both the forward and reverse reactions equally. So there's no shift from a catalyst. And finally, if you have an irreversible reaction that goes to completion, this means that you can never reach equilibrium. You will always have just products forming. And you can force a reaction to go to completion by removing the products. Alright, so this is all I wanted to say about this topic. I know that this was pretty in-depth and there's a lot of math that goes along with it. But again, I'll put up some practice for you to do, and we're going to do lots of practice in class. And so hopefully you'll be good. Alright, thanks so much for watching.